Okay, so it's 3 o'clock. Let's get started. Um, so today's agenda is to talk about self-supervised learning and and the attention and self-attention mechanism. Probably you guys have heard of this due to the recent Chat GPT blow up. We'll talk about the transformer architecture in a little bit of detail, and then just go over what kind of foundation models are being used today that that are powering all of this chat gpt, um, google gemini, etc. I think I'll close the door maybe. Okay, yeah, if someone not, a- not able to hear me, just let me know. So why do we need other kinds of learning? So far in the course, we have done supervised learning, where you have X's, you have Y's, and you just train a model to learn the XY relationship. So why do we need to use other forms of learning?
I think as we talk about this, if I believe there's a lot of human able to
Mm-hmm.
unsupervised. Yeah. Parts.
Yeah, so you don't need to do some manual effort like labeling stuff. Also, like if you look at how we learn as humans, we don't get supervision on a lot of things. We mostly observe things. And so babies, they are not given a label of all the images, right? They're once told, okay, this is a cow or something, and then they just figure it out by looking at the behavior. So we learn by observing a continuous flow of data. We see everything that's going on. We see that, okay, someone opens the door, someone closes the door, why we close the door. This is all making inferences in real time, like what is the logic behind each and every action. So that is how we make inferences. So the data will follow certain rules. So maybe when we see a cricket ball, like which hurt my hand recently, it flows in a projectile. We make inferences about where the ball is going to be. So those are the rules which are like immutable. They don't change. There are things like language grammar. When we are speaking or talking to someone, we learn through observation or by overhearing other people that what are the rules of the grammar or just general human behavior. Like if it's a class, most people will be sitting, one of them will be standing up. So this is a typical human behavior which we are not specifically supervised to learn. We observe it and then we just make inferences about things by our experience. So we make this world model by figuring out these rules, and this is mostly done by observation. Then we make predictions about the environment and make decisions. So there could be some weird guys here who can like just stand up and start dancing, but that is an atypical behavior. We mostly make our decisions like if you are students, you will just sit here and then learn mostly. So that is how we make decisions. But so far, what we have learned in this course is you have XY pairs, you train the model and then ask it to predict the Y for a given X. That is not natural mostly. So there is this thing called self-supervised learning, which got traction, I think, 5, 6 years ago, or maybe even more now. And unsupervised learning is something that we'll cover later in the course. It has been around for a while, and that basically deals with how to model structures and data, and it is not specifically told what to predict, uh, but we are not uh, giving it any signals per se. So let's say if you want to find out what is the um, probability density function of a distribution, there are unsupervised methods to do that. And you are not predicting anything specific about a given X, you are just learning the structure of the data. So that is something that we'll cover later in the course. But self-supervised learning is that we find out some naturally occurring pattern in the data, and then we train models to predict that. So this has been tried around for a while, and it has been shown to work a little. And then we found out like very efficient model architectures and learning techniques, which made these self-supervised learning basically the meat of what we see in online models nowadays. There is also semi-supervised learning. Uh, this is typically used when you have a lot of unlabeled data and some labeled data. So you try to do self-supervised learning on the unlabeled data and then use a little of labeled data to make inferences about a lot of unlabeled data. So that is semi-supervised. So in this lecture, we'll be focusing on self-supervised learning. There are multiple ways by which this is done nowadays. There is a generative part to it where you generate some the data itself by some transformations. There are discriminative tasks, like you can have a self-supervised objective which is discriminative in nature. I think discriminative and generative was covered in the last lecture, so you must have some idea. And there is like, so far we only worry about a single type of data. Let's say if it's an image, we only worry about images. If it's a vector in some space, we only worry about that. But there are models nowadays which deal with multiple sources of data like audio, video. Um, uh, so you will have multiple inputs, multiple forms of inputs, and you can make predictions about all of them together. So let's talk about generative self-supervised learning. So I guess if you was autoencoders covered a little in class, it's a basic, um, you you take an input which is inherits an image, you pass it through some transformations, you get a bottleneck of representation, and then you try to recreate the input using that representation, and you train it on a lot of data. So what is this data here? Like, it's just an image. We don't have any training supervision here, right? So we can just use unlabeled images and train autoencoders to just recreate them, recreate the input image. So what this is doing is it is bringing the original high dimensional image down to a small feature space, and then it is decoding that feature space again back into the original space. Why would this be any useful? Is we hope to learn like a representation space which captures something meaningful about the data. So let's say this feature space captures some abstract concepts in this image, which is like a cat. It has two legs or whatever. It has two eyes. There's green background, and we hope that these features are encoded in some of these dimensions. So after we do this pre-training, we call this pre-training because we are not exactly using any supervised labels. So we just use images and train this autoencoder, and we get this representation space. Now let's say we have a new image. We pass it through the encoder, we get a representation. What can we do of this feature space? So remember we talked about like semi-supervised learning. If we have labels of a small number of images, we can just like train a linear layer after this representation space to classify it into one of these classes. So then because the feature space, if it is supposedly very rich, it will it will learn that, okay, this feature is supposed to predict cat, this feature is supposed to predict a grass or something. And we need a very few number of labeled samples to make a reliable classifier. So it has been shown that if you pre-train stuff like this, and then only with a small number of samples, you do supervised learning, then on unlabeled images, you can just pass it through the encoder, which would remain fixed, and just pass it through the linear layer, and you will get a correct classification. So there are other ways you can do autoencoders, like self-supervised learning. One of this is the converting a grayscale image into colored image. So this is very simple. You will have a bunch of colored image. images, you just convert them into grayscale images and then pass the grayscale image into the input, um, and get a colored image as output. So um, what would the network have to learn to make this kind of prediction or like this well, do this task well? Any ideas? You're passing it a grayscale image and you're asking it to generate colored images.
We create ours.
Yeah,
So we have it already.
yeah, yeah. Not the grayscale. With the original, so we have this colored output. So this is essentially our Y that we wanted to predict. And whatever the network predicts right now, we will just take a loss with the original colored image. So yeah, once we do that, what do you think the model will encode in its representations? Yeah, something like that. So if it sees a structure of a butterfly and it has seen like these kind of colors in a butterfly, it will learn, okay, because there's the structure, it is most likely a butterfly, and now I should paint this color into this image. So in doing this task, it has learned the structure of butterflies and everything, right? So the representation space, the feature space is, we hope that it would learn features that correspond to these structures and like something more meaningful about the data rather than just pixel values. There's another yeah.
Restriction on the model.
Yeah, so actually this colorization task is not done, typically it's not done using a simple autoencoder like this. There is something called a unit. So what a unit does is, so this is the representation space, right? And so what we are asking a normal autoencoder to do is condense all the information that is present into this image, into this space, and reconstruct it back. So it is like a task where you're compressing the data a little bit and compressing it into this space. But if we are just doing colorization, let's say we don't want to use this feature space, we just want to do colorization. What we can do is pass uh, these layers, the output of these layers, and concatenate it here so that it has access to these features as well. Uh, so it is done at multiple locations, and that's why, because this architecture looks like a U, this is called a unit. What this does is, like, you will have, when you pass the loss here, right, you will have gradients going in from the side. It won't have to go through this small bottleneck. It can pass directly from here to here. So it will learn features at this position, which is meaningful in coming up with the representation, but also meaningful in coming up with the reconstruction, which would help in the reconstruction. But once, yeah,
Go through the object and also go through the.
yeah,
So it's like a residual.
yeah, it's a residual connection. The problem with this is now you cannot use this because if you want to, like, you can still use this, but now the bottleneck is not constrained to restore all the information that is present in the image.
But it's also passing.
Yeah. So it might be like just using this to reconstruct it better, or maybe using some part of the structure of the image from here and the rest of the stuff from here to reconstruct it well here. So yeah, this is like if you take a deep learning course, you'll learn more about this. Um, okay, so yeah, there's a colorization. There's another generative task called inpainting, where you just remove parts of the image and ask it to fill. So now the model will have to learn structures in the data to be able to do that well. There are discriminative self-supervised tasks like let's say you have an image, and you give it a center part of the image, and you break it up into 9 pieces, like these 9 pieces. um, and then you just ask it to predict which direction this is supposed to lie. So let's say if you are giving it this box and this box, then it is saying that okay, it is supposed to lie on the third location. If you are given it this box, it would predict it's supposed to lie in the right next to it. So what this is doing is it is doing a classification, right? You pass these two images into the shared weights CNNs, and then you concatenate their representations, and then you ask it to predict which is the direction the second box is supposed to lie. And what this is supposed to capture is again the same representation. So here what we did was like we created the labels using this positioning, which is very normal to do. Like you can do it algorithmically. So we don't need to label the data, but after this is said and done, this CNN will produce representations of that part of the image, which are hopefully meaningful for downstream tasks. So this is a discriminative task which we can do. Similarly, we can also just pass all these 9 images as a random permutation, and then take their outputs from this convolution and ask it to produce which of these permutation it is. So this is also like, okay, it's maybe not better. So it is asking it to rearrange, uh, like what is the original, if it is like 1, 2, 3, 4, 5, 6, like this, and you just jumble it in some permutation and ask it to predict what is the permutation. So that will be if there are 9 images in a single image. Like if you cut it into 9 pieces, there will be 9 factorial permutations. So you will have 9 factorial number of classes here. So this is again a discriminative task, which you can create out of nowhere. Yeah. No. So the permutation, it will have to identify what is the permutation that led to this representation. So what we have done is it jumbled according to, let's say, I'm index 64, you had this permutation. So now you took 1, 2, 3, 4, 5, 6, 7, 8, 9. You jumbled it according to this permutation, and then you passed it through these layers. You get all of this, you pass them through FC layers, and then you ask it to predict what is the permutation that led to this. Uh, I don't know. It's probably this.
Because like, no, I so like the one conflict. Two is
Who is this? This one.
so like, so the correct is 9, 4, 6, 8.
Yeah, this one. So what they have done is to put the 9 over there, 4 over at the second position, and so on. So all of this is this permutation. And because it is in this order, it has to figure out like how this order came to be. Uh, yeah, it's after scrambled. So you have this like you just order them you want, like order like 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you jumble them according to the permutation, like one of those 9 factorial permutations, and that's how you pass the as input here, right? So this is the jumbled version that you pass it, and then ask it to predict which jumbled version it was.
So it's not prediction of the original. The original.
No. It is just learning like what is the spatial correlation between all of these parts of the image. So for it to learn that, it must learn some features. So let's say this is the wheel of the car. This is the windshield. So the network must figure out that these two will have to be in a certain position, a certain orientation. And for it to figure this out, it will have to learn some features that are invariant across all of these permutations. So if you found out that okay, uh, the sixth went to this position, right? This is the position which is the fourth went to this position. So now it found out that this is the wheel portion of the image and this is the windshield portion of the image, but they cannot be adjacent here. So what would be the permutation that has caused this discrepancy?
So is that like, so our input is scrambled order,
Yeah,
predicting the scrambled order.
yeah, we are predicting what is the index of that permutation. So this set will be fixed. You will list out all the 9 factorial combinations. You will list out all the permutations and just randomly select one of them and then jumble it according to that permutation and ask it to predict the index of that permutation. So in that way, it will just figure out like what is the relative position of each part of the image and so on.
Uh, Denting the scrambled order. Now where it's just random. So this is trying to create more training data, right? So think about that. So you're creating exactly more training data without any labels. So by just generating those mapping, you just shiftly freely get this data, and this part is corresponding to this part in a random. Then to create this kind of feature representations. It's not a specific predicting task, it's just for learning features.
Maybe we'll take it after the class because
Yeah.
in interest of time, I will like take it in detail. So something like that is like rotation. You take an image, you rotate it in one of the 5 settings, and then just ask it to predict which rotation it is. So it will have to learn like what is the natural orientation of uh, things in an image, so that this rotation is only possible when this is the particular rotation. Um, so if you talk about which of these methods is best, it's not clear. Like we don't know any theory about it. So we just need to rely on experiments. Whichever works best is typically used in industry actually. So there are many choices of experimental setup, and this is something that you will have to do in homework 3 as well. Like figure out what is the better model architecture, what is some hyperparameters that you can tune. And we don't have a good theory about how to select the best one. It is just like you figure out something which works well for the task that you want it to do well. So let's say if it performs well on the validation set, then you just pick the best model architecture, model hyperparameters using the performance on the validation set. If it is like fairness, you evaluate on that metric and just pick up the best architecture. Uh, Regarding multimodal SSL, there are so many works in this domain as well. Um, we will not go into the detail of these, but you can take a look at all of these papers which talk about how to combine different modalities of data together. Um, so, so in image, we have talked about image in the CNN part, and that is typically a height cross width cross channel kind of an input. In with language, it is a 1D signal. So we will just have an L length sequence, and C is the number of channels, which in case of language, it just corresponds to what is the vector transformation of the input. So if it's a word, so we just we take what is the representation of that word. We'll talk about it like how this embedding and everything is calculated a little bit, but yeah, this is a different kind of input than image which we have seen so far, and because it has different inductive biases, it will have patterns in the 1D signal domain. It will not be like a single vector. If you suppose C is just one, then it's just like an L length vector, but it is not a vector because those vectors the dimensions are typically independent, but here you will have a sequential pattern in the data. So why do we want to do self-supervised learning on images or self-supervised learning on text, or like a pair with this when we are talking about multimodal models. Because on the internet, you'll find a lot of images which have captions with them. So this is basically, it is supervised in some sense, like someone has written that caption, but that is not done in an in a fashion that, okay, this is for this task. Someone just wrote a caption for an image, and now we can source that data. So we will have image and caption pairs. And this is like very easily, you can get this on the internet, tons of images like this. So language is also important because like a few words will be able to describe the image well. Although it is said that, you know, an image is worth 1,000 words, but like a few words can describe an image quite well. So that is, there is a semantic density, like you can condense information in a small amount of input. And there's universality, which is, if it's a good language, then you can describe basically anything with that language. So there is nothing that you cannot express in that language. So if you have any image, you can potentially write a caption for it. And there is scalability because of something I talked about right now. Like there's tons of images on the internet with captions. So it is very easy to source this data. So there are models, multimodal models like Clip, which is from OpenAI, where you have an image encoder, you have a text encoder, and then you have this, it is asked to create embeddings such that those two align. Um, and there is a contrastive loss, which says that each image predicts which caption matches. If it's a different caption, then it would be the embeddings would be made such that they are as far away from each other as possible. And if the caption matches, then they are taken closer together. So in this way, what you end up doing is, for an image, you will generate an embedding, and for a given caption, you will generate an embedding. And if the caption matches the image, you are likely to end up in the same area in the representation space. And this is done for like 400 million images. So you train on a lot of data for a lot of days, and it just learns to perform quite well. So what this can be used for is, let's say you have this can be this can do something called zero shot classification. So remember, in autoencoders, we took the image, we got a representation, and then we had to uh, train a single layer on a few images for it to be able to classify any new image. Here, what we can do is just take an image and then uh, create a caption, like a simple caption. Let's say we want to do classification. So this is the dog. We can take all the classes that we want it to classify, and then just pass all the text encoder, and like through the text encoder, this caption. Like, is it a photo of a dog or a car or a bird and whatever? So you will get multiple different text embeddings for multiple different classes, and then you can just take the dot product, and whichever is the greatest, you can classify it. So this is something called zero shot classification, because you're not even training on one instance of a labeled text. Is this intuitive? Sorry? So these are, let's say you want to classify an image. You have a bunch of classes and the images of one of these classes. Then you create a caption, which is like a photo of, then this is like a blank thing with all of these. You pass all of those captions through the text encoder. You will have multiple different text embeddings, and you pass the image through the image encoder. You will have the image embedding, and then you take the dot product of all these vectors. So image with T1, image with T2, image with T3, and so on. So if this image can be described by this caption well, which is a photo of a dog, then it should have a high dot product.
So the concatenation of where you match it. Analyze T1, T2.
Yeah, this is I. This is like image.
So that's.
It's not concatenation. You can just assume that this is a vector and these are all vectors. And then you just take dot products of these vectors. So these are these values. And this you can interpret as like something like a classification score, like a softmax score, which you get from your classification model. This will not exactly be softmax like it or like probabilities, because the dot products probably won't add up to one. But whatever is the highest, you can put a softmax layer on top of this vector to get the class probability.
So, specific.
Yeah.
For each and then they could be different, and they also create different wording.
Yeah. So let's say you have 400 million images and corresponding captions, right? You source them from the internet. Then you take a bunch of images, you take the corresponding captions, and you also randomly sample some other captions. So those are all the captions there. Now you pass an image, you will get all the image encoding of all those bunch of images there. You pass the captions, and you will have a bunch of caption embeddings. Then you take the dot products, right? So if the image encoding matches the text encoding, which is the corresponding caption, then you ask it to make it as close as possible. So, and if it is like the caption does not match the image, you ask it to make it as far as possible. So this is something called a contrastive loss. So it is making the embeddings contrastive in the sense that if they are very similar, then they should be close. Otherwise, they should be as far as possible.
What is the last one?
I don't have it right now, but it is basically you sum over the whole batch, and you take. Let me try to write down a simpler version of that. So it is like if it is close together, then the dot product should be one, right? So for the positive class, you should have something like the one minus IP dot and plus all the negative captions. You will add their dot products. So you want them to be as far as possible. So if there's any value in IP.dp, you want it to be close to 0. And for this, you want it to be as close as possible. So this will be, um, if it is less than 1, then there will be a loss. So in the perfect case, you will have this equal to 1 and these all equal to 0. So the loss will be 0.
For each, okay, we get what we predicting on what.
No, we are predicting the embedding of the whole caption.
So we're predicting, so like, for example, this, we're predicting.
No. So that is a classification case. Like this is how we would do zero-shot classification because we are generating a caption out of thin air. Like this caption does not exist. Here we already have the text corresponding to that image from the internet. Yeah, so it is a wide variety of captions. Maybe someone captions an image of a dog differently. So, but it is still an image of a dog. So if let's say there's variety in how a caption of a dog can be generated, this loss will take care of all of those and make them closer together.
The next. Here. Down image. No different case.
It's just one image. Yeah. Yeah, you are doing zero-shot classification of an image. Yeah. So So any other question? Okay, so moving on. So we can also do self-supervised learning only on text. Like this was clip was on image and text pairs. Why only text? Because what is even more accessible than image and caption pairs, do you think, on the internet? Okay.
I don't know. Yeah. Things in people. So, make sure you make lots of speech. I don't know. It's easier.
Yeah, so let's say you have speech.
Yeah.
There are multimodal models that do speech alignment in videos. Let's say you just have speech and you have a video and you want to align where a word is being said. So that there are models that do that. Uh, for something like a classification, I think if you have text which is more interpretable, and also you can come up with these captions very easily. I think it is an easier way to do classification. But let's say you had a bark, right? You had audios of different animals, and you can just pass the same audio and see which one it aligns best with. Uh, an image of a dog or like a video of a dog. If it aligns well with the video of a dog and a bark, then it would have a higher dot product and so on.
Yeah.
So you can take like YouTube videos, take all the videos out, take the audios out, and then align them together. Similarly.
So, yeah, you, so. It's two modalities at the same time. So either we do email or you run it. Run it to you.
For this task, I think that would be an overkill. Maybe for some tasks, you need to align all of three together. Let's say it's a caption generation task, or maybe let me think where we could have all three modalities come together. Yeah, let's say we want to make audio for a video that has been subtitled, right? So you have a given subtitle, you have a given video, then I don't know if you can generate it using like something like the zero shot thing, but I know models that do this. Like you have a given video, you have a given text transcription, and then you generate audio out of it, which syncs.
So I guess
Yeah, context switching. Yeah. Yeah, for classification, like two inputs are more than sufficient, as we saw here. So, yeah, so what is even more accessible than image caption pairs on the internet? Yeah, just text, right? Yeah.
so
Okay, like Wikipedia text you're saying.
for like some
Okay. Yeah, that is fine. But like Piazza is also closed in some sense. If you just have a web crawler which crawls through all the websites in the world, then the most widely accessible form of data that you will have is text. So so this is something that people figured out, and then they thought, okay, let's just train models on text and just not care about images anymore. So can we use SSL on natural language text to learn transferable representations? That is a question that these people asked. And they one-upped one thing like, can we use SSL to develop models with which have world understanding? So is it like if you just give it text data, can it understand those things which we talked about at the start of the class, like physics of the world or like human behavior and so on? So turns out, like, if you look at ChatGPT, it it understands a lot of things quite well. So it is possible to just use natural language text to come up with a decent understanding of the world. Um, yeah, I think RNNs were covered last time. So there are sequence to sequence generation models in RNN where you can use only text. And let's say this is a machine translation model, which takes as input in something like an it's English, and then generates a French translation of it. So what this does is it takes the input, pass it, passes it through the RNN layer, and then generates an output, then passes it again through the RNN, which to take the second input and so on. And once it reaches the end, it is asked to generate uh, the translation. So this can be trained only on text, but you still need supervision, right? You need labeled pairs of translation as well as the original language. Uh, there are something called like generative RNNs, where what you can do is just train it to predict the next word. So we feed the words one at a time, and then we just model this distribution, which is what is the probability of the next word, given that you have seen this whole thing in the past. So if you pass it the previous thing like the brown dog, then it will generate a probability distribution over all the words, what could be next. And ran would probably have a high probability. So it uses a predictive head um, and generates a probability over the vocabulary. And this is like if you train an RNN based language model on this next word prediction task, you can come up with something like this, which is not very coherent. Like if you train it just on Obama speeches and ask it to generate something, it it typically it is found that it does not perform very well. So there are other things people have tried, like LSTMs. LSTMs have better memory management, or you should say like context management. Like there are multiple gates in an LSTM. We will not go into the detail of LSTMs because that is better in another course you can take. But people came up with this model called the Elmo model, which uses both forward language and backward language model. So there are things in English language where if you just saw the context from until before this word, it is not sufficient to predict this word. You would have to look at uh, the sentence afterwards to figure out what is the best for the worst word. Yeah. So this uses both forward language and backward language models to come up with representations, and you can concatenate the hidden layers from both these models, and then sum the vectors. It's basically learning representations from this next word prediction task, but this is next word both from the forward as well as the backward scans, and these representations have been found to perform well on multiple downstream tasks. So this is something like an autoencoder. You train it on language like a large chunk of data, and then you find representations of the words or sentences, and then you can use those sentences for things like use those representations to train downstream classifiers like sentiment analysis and some other types of classifiers. We'll not go into the detail of these, sorry, Elmo models. So we'll just now talk about what are the problems with recurrent models and how we can fix them. So advantage of RNNs is that you can have a single model and you can use it repeatedly. So it does not depend on the input size, and it can also keep some context from long ago, in theory, at least. But there are weaknesses because recurrent computation, if you perform one computation at a step, you need to wait to perform the next computation before the first is being done. So if you want to parallelize it using computer resources like GPUs or whatever, it is not possible to do that because the design is serial by design, basically. And they also quickly tend to forget portions of the input, because if you look at this, uh, at the end, you get one single context vector of the whole input, and that you have to interpret for, let's say, making this whole translation. So, so then there was this architecture, which was, I think, 2014, where they came up with something called attention. Um, and this proved to work quite well. So we'll just take a look at it in a little detail. Yeah. So if you look at the RNN, right, it takes a hidden state and it takes an input vector. So initially the hidden state is like an initial hidden state, and you take an input vector, and it performs computation, and then it produces an output vector. Um, so this output vector is uh, passed along to the next step as the hidden state, and then you have the input at the second step to pass as the input. So, and this keeps on repeating. So for a translation model, what happens is you have the first step of the encoder, then you get a hidden state, you get the second step, you get a hidden state, third step, then you have a final hidden state, which is the context vector. And then the decoder is supposed to extract information from this compressed context vector to do the whole decoding. So what these people figured out was, what if you keep all the hidden states in memory, and then at each decoder time step, you look at what are the hidden states of the input, and then you try to figure out which of them is most important for decoding at this time step. So there is a score function, which is basically the attention, which finds out, which takes the decoder's input state and all of the three hidden states and assigns them each a score. And then you softmax those scores. So like this increases the probability, or like this increases the weightage of the high scoring ones and decreases the weightage of the low scoring ones. And then you add all of these hidden states together, uh, weighted by their probabilities. So then you have a mixed representation of all the inputs uh, based on what the decoder thinks is necessary for decoding at that time step. So, so if you look at this, let me see. Yeah, you start with when you have all the three input vectors, like H1, H2, H3. The decoding starts with a token, like it's a token instead, which is the AND token. And then there is something called H init, which is also like an initialized data representation. And you pass them to the decoder, you get H4. This H4 is it's the context that you get out of the decoder from the initial state. Now with H4, you you perform attention with all the three input vectors. So this is taken along with the first one to get one score. This is taken along with the second one to get this score, and so on. So however many inputs you have, you get a vector of the scores that you get for all these attention. Sorry, all of these hidden encoder states, and then you softmax them and add them together. So after you got all these values, you will use a softmax operation, and then you add the vectors weighted by the softmax values, and you get this. So this is the final output, which is a context vector that goes that is very specialized for this decoding step, and this makes the decoder basically perform much better because it knows what to attend to and what to decode at that time step. So you got this and you got this, you concatenate them together, pass them through a feed forward layer to get the output. So this is the output which it got, like it's the translation of the original sentence at the first step. Then you take this output. Now this will go as the input to the decoder again, which was initially and which just denotes that you need to start decoding now. So that input goes to the decoder again, and this is the hidden state which goes into this again. You get H5, and you repeat the same process again. Like H5 will be attended to by all the three input encoder states. You'll get a softmax, you'll weight them, and then you'll get a specialized context vector for this time step. So what this is doing is basically, if you didn't have this attention operation, you would just have a single context vector here, which has to be used by the decoder to perform all of these time steps, which is basically a bottleneck for the context. Yeah,
8, 4.
yeah, we are using H4. Like this H4 goes here, figure out the first. Yes, this will be used in the next part, and this is used to get this context vector. So you use H5 and you take this, the first one and you pass them. So here actually, if you look at the
4 to the JHU.
yeah, so you H4 is the H init for this step.
Oh, I see.
Yeah. So what this gives the decoder is a flexibility to come up with a context that it thinks is important at this time step. But this is again like still RNN. Uh, so this performed quite well, and then this took off. So just to summarize, like this basically decoder gives itself a choice of what context to look at a particular time step. So if you look at the weaknesses, what does this solve? The attention mechanism. We talked about these weaknesses of the RNN. So what does this attention mechanism solve? No, you cannot paralyze it. This is still LSTM or like an RNN. It's not the transformer yet. It's just an attention. Yeah.
Doesn't.
Yeah. So this is what it fixes. Like you you don't tend to forget very easily because now you can attend to what you want at that time. Yeah.
You just don't know that how it works there. What exactly is it? Something. Sort of as a string, you just like.
Yeah. So this is the decoder, right? You have something similar in the encoder, which is a fixed model. And now you can give it an initial state and an input, and it will produce an output. You can continue doing this for as long as you want. So because this doesn't have any restriction on the number of inputs, if you give it 5 time steps, it will just take 5 H1, H2, H3, H4, H5. And then when we pass this AND token, which means that, okay, now you need to start decoding. This goes to the decoder. So you can decode it for some time step. And what is the output that you get? Let's say when you are training it, let's say it's just a translation task. So maybe the input in English sentence is 5 words, but the French translation is just 4 words. So after the 4th step, you will train it with a 5th one, which indicates that now you need to stop. Like this is the end of the translation. So when you ask it to generate a translation, it will also generate a stop token where it will indicate that, okay, now you stop. This is the translation.
So is the end? Is
Yeah,
the token that comes out of the state, is that a fixed way
for every input that we put in.
No, it's not fixed. So you can have like 10 words, right? And after that you put an end. And when end goes, then it knows now I need to start decoding. Yeah. So these are like special tokens which you use when working with natural language because nothing is fixed there.
So basically, I'm feeding input tokens. And the input state is building up this context, which is basically the foreign matrix.
Yeah.
Actually have pass, which tells the encoder to say, okay, I give you all the context. And
Mhm.
then the decoder takes over, takes the context and then encoding.
Yeah.
Starts
Decoding. Yeah. These steps can be separated in design as well. Like you can just, let's say you can fix the encoder part and then pass it only the encoder tokens or to encoder inputs and then collect all the representations. Like these are the hidden steps, right? You can collect it for as many input tokens you have, then just stop and collect them. And the decoder can be completely separate because there's no connection between them. Uh, and then this called gateway, but it can basically be a start for the decoder, right? This is just a special token for the decoder to uh, set itself to start decoding.
So if I had a set of those tokens, I would need it next input, I could just feed that right to the decoder.
Yeah.
So is the reason that these models struggle with next line because the decoder can't start and decoder is finished, like encoding all the context. We can't start decoding stuff and it'll be finished encoding all.
I will come back to this, and this is not the language model that you're thinking of, and it is not the context length that you're thinking of. That happens in a different architecture called transformer, which we'll just go into next. But this is the original attention which led to self attention or the transformer. So this is an attention between the decoder steps and the encoded all the encoded steps. There is something else which we'll cover next. So you found out like this takes care of the forgetting part because you don't have to compress everything into a single context. You can just use whatever context you want with this attention. But it is still slow because it is still recurrent in nature. You cannot parallelize computation. And there is still a problem of exploding or vanishing gradients because this is again like taking steps back in time. So this paper introduced something called self-attention, which is, yeah,
Sequence before this,
yeah,
like the famous self-attention.
yeah, yeah. It's an inspiration. Like that paper is an inspiration to the self-attention. And actually, that this is still not that paper. This is still not attention is all you need paper. This is the paper which introduced self-attention, which is used in that. So that paper basically showed the attention is all you need paper showed that you can solve all of these RNN problems with just attention, which we will take a look at. I think we'll not have enough time, but like let's see. So this is the paper which talks about self-attention. And self-attention is like if you look at the encoder of the previous this one, right? These inputs, these are also a sequence, and there might be different parts of the inputs which have more significance to other parts of the input, but nothing of the attention sort is applied here. It is just between the decoding and the encoding stage that you use attention, right? So in the self-attention paper, they did it in the encoder and the decoder steps separately as well. So what they do is like the encoder will also look at all the other encoder steps and just figure out which is more important. And then you use additional feed forward layers to find out what is the best representation. Like it's just another layer of attention on top of it. So this is the paper, attention is all you need, which brings in the transformer architecture, which will use self-attention as well as attention. So we'll take a look at it in detail as well. Yeah, and I forgot to mention this thing. So all of the attention that you saw here, right? You take H4 and you take H1, H2, H3, and then you're taking H4 and H1 and calculating an attention score, right? So that is done in this paper using a neural network, which is A. A is a feed-forward neural network, which takes in two vectors, H4 and H1, and gives it a score. It also takes H4 and H2 and gives it a score, and so on. So this is a feed-forward network. It's not any dot product or something. So which will change in the transformer architecture. So right now we saw that the encoder was an LSTM or a RNN. The decoder was also an LSTM. In the transformer architecture, what they came up with, you stack multiple encoders on top of each other, and then each encoder, you have multiple stacks of decoders as well, and each encoder has something called a self-attention layer and a feed-forward layer. So between the encoder and decoder, there's also something called encoder-decoder attention, which is similar to what we saw in the decoder in the attention previously, which was using the H1, H2, H3 from encoders and comparing the attention for the decoder time step. So that is something that corresponds to encoder-decoder attention, but the self-attention layers are something different. So let's see what those are. Uh, So you have a sequence of words, right? And these sequence of words are represented by some vectors. There are You can take a whole lecture on how to better embed those words into a vector. But let's assume that we have those vectors. So all of these are fixed length vectors which encode a single word. So what we do with the encoder is we pass them through the self-attention layer. We get some output of the self-attention layer, and then we pass them through feed-forward layers to get the output of the encoder. So let's take a look at the self-attention. What self-attention is doing is, let's say you have this input. The animal didn't cross the street because it was too tired. So here, what is it referring to? Is it referring to the animal or the street? Yeah, it's easy for us humans to figure this out, right? But for the for language models or something like that, it may be confusing. Like, what is the object of this reference, which it is referring to? So, if you look at the attention, um, this is after you've done all of this self-attention training and everything, you will figure out that it is referring to the animal at most, like at the most. So it has learned that what is the part of the same sentence which is most relevant to this token or this word. So this is an inductive bias, which is probably very beneficial to model language because you can have different parts of the sentence which are relevant to very different part of the other sentence. So how this is calculated? So you have, let's say, inputs, and these are two different words, x1 and x2. These are two vectors. There is a matrix called WQ, which you can multiply these vectors to, and you will get uh, this WQ, WK, and WP. You can multiply the inputs, and you will get this corresponding vectors called Q, K, and V. So these are called queries, keys, and values. These are just like naming conventions, but there are intuitive ways to understand what they mean. So let's see the input. Um, yeah. So let the input be thinking machines, right? So you have the first input, which is a vector for thinking. You have a query vector because you multiplied it with the WQ. You have the keys, and the value vector. So the self-attention step here is you multiply the queries and keys together. Like you take a dot product of the two vectors. So queries are essentially a question what is the question that you want this token to ask. So let's say if we are just looking at the word thinking, there is a question involved with this word, that is the query vector. And if we multiply it with k1, which is the key, which will correspond to the what is the answer for this question, if this is the question, then q1 and k1 would have a higher dot product if the question and answer match. Similarly, you can multiply q1 and k2 together. So if they also have a high dot product, that means it is very relevant to this, or the question has matched the answer a little bit, something like that. And you do this for all the tokens in your input. So you will have q1.k1, q1.k2, and then q2.k1, q2.k2. So you will have a n cross n uh, score matrix basically. Uh, then there is this divide operation, which is basically it's an design thing which makes gradients flow well and whatever. It is not part of the intuition, but you just divide it by this value and then take softmax. So after you take softmax, it is similar to the softmax you took previously in the previous attention. And then there is this value vector. So which corresponds to what is if the question and answer match, what is the thing that we should take away? And that is the value. So we multiply the value vector with the softmax and then add them together. So that was in the previous step, like in the previous attention thing we saw, we were just taking the softmax and then multiplying it with h1, h2, h3. So h1 was the original thing. Here, if we did not change this to v, we could have multiplied it directly with x1 and we would have gotten the same thing. But we are doing another layer of transformation, which is we are asking it what should be the value we should take out from this step if the questions and answer match. So you ask the first question to the uh, first token, you get some response. You ask the first question to the second token, you get some response, and then you add all of those takeaways together. So you will get a final z, which is the sum of all the values, and that is it. That is what self attention does. You This is for the first token, right? So for the first token, it is attending to all of the other tokens. The second will also attend to all of the other tokens. And all of this will be added together like V1 and V2 to get Z1. And then you will have a corresponding for the second one, which will give you Z2 and so on. So these are the outputs of the attention layer. If you look at it in the form of a matrix, you can consider the inputs the sequence of inputs as a matrix. And then you multiply it with WQ, you will get a sequence of queries for each time step. That will be the matrix Q. And similarly, you will get K and B. And then you do this operation. This is the self-attention operation. You multiply the queries with the keys, which is what are the questions all of these input words are asking, and what are the answers all of these words are presenting. And if those match, then you get high values. If those do not match, then you get low values. And then according to the weights, like this will give you a weight, you take the softmax and then you just add to the value and take away the output. So this is just an inductive bias at the end of the day, which helps you model language better because it is like you know what part of the input is attending or is significant for other parts of the input. So if you just do it for one layer, you will have one sets of questions and one sets of answers and one sets of takeaways. But you can do this for multiple heads, which is just like you add this thing together. So you can have multiple types of questions. Uh, so let's look at the first example with this thing. So the question here would be, the animal didn't cross the street. So if the question was, is this word present in this word? Like that could be one question. Then these two would have or like a load overlap because it didn't cross the street. And there could be other questions like is this word and this word match in the state of the objects that they are representing? So like the animal and tired, then it would have a high overlap and you will have a high attention value because it is asking a question whether this object and this object has yeah, these are all generated by backpropagation. So you can like I don't know if you were here in the CNN lecture, but the CNN you have the filters. You can hand design the filter, but we don't want to hand design filters because we are not sure what the features are. But this query and everything is learned as part of the training.
So the queries are initialized.
Yeah, they are initialized at so the queries are not initialized. The WQs are initialized. So when you multiply it to the input, it knows what query to ask. So, so these WQs are randomly initialized after you've done all the training. These no. So X1 is multiplied with the first column to get the first value. X1 is multiplied with the second column to get the second value. So yeah, it's a weight matrix. Yeah, yeah,
So like in CNNs, we do feature learning.
yeah.
Like,
In this architecture, yeah. So these are basically you can understand it as like what are the weights that transform the input well uh, at the lowest level. But as an intuitive understanding, this is better. Like you have some questions you want to ask, you have some answers that you have collected. If the questions and answers match, you just take the value away with a high weightage. So that is the whole thing about this. And so you can have multiple sets of questions and answers, and you will have this multiple attention heads. You will get multiple outputs. So you can concatenate all of those outputs together from multiple heads. So this was the output from the one attention head. If you remember, then if you have 7 or 8 heads, you will concatenate them all together. And then you can have an additional matrix called WO, which will transform this into the original uh, input space. So this transforms the input in a way which is relevant for whatever task it has been trained on. So this transformer architecture was originally introduced in a paper which did machine translation. So you had English to French kind of stuff. So you had encoders where you will give it the input in English. It will figure out what questions to ask, what answers to present, what values to have, and then you will have this uh, decoder step, which will transform this encoder representations into the French or whatever language. What? No, so all of these are not shared. Previously in RNNs, they were shared matrices, right? Because you were repeating everything on the same model. Here, everything, if you look at the initial, uh, yeah. So all of this self-attention, this is just this block of an encoder. Then you get the Z's, right? You transform them using feed-forward neural network. And this is basically, again, just adding another layer. Just give it more complexity. Yeah. No. No, it's still not there. The feed-forward is something else. The last layer, which you get like the Z here, right? You get Z's from multiple heads. You concatenate them all together. You multiply it with WO, and then you get a Z. That is the output for um, one input position, right? And then for these Z's, you will have this for everything, like for all time steps, or I should not say time step, like all the words in the sequence, and then you multiply it to the feed forward layer. which gives the final output. The feed forward layer is just there to add number of parameters so that it is just over parameterizing the model so that it has more flexibility to learn any complex functions. So after this thing, um, yeah, so after you've done all of these encoders, you can stack them on top of each other. So after you get the output of the first feed forward layer, you will still have all the same encoder positions intact, and then you can stack another encoder layer, and so on. Finally, you will get some encoder outputs, right? Then there is decoder, which has the self attention layer. Again, one second. The decoder, the encoder has self attention. Then there is some. I don't think we have time enough to capture everything. But like there is add and normalize. There's also residual connections. These are standard things in deep learning architectures that you do to make them perform better gradient flow and whatever. The final thing you get out of the encoder is passed to the decoders for encoder decoder attention. So encoder decoder attention is something that we saw previously, where we were using H4 and H1, H2, H3. Those were from encoders, and H4 was from the decoder. But the decoder also has self attention. But this is a masked self attention because we don't want it to attend to anything in the future, because it has just decoded the first word, let's say. We don't want it to attend to anything that at the end, because we have not decoded it yet. So I think maybe I'll cover this up in the recitation this week, whatever is left. So yeah, feel free to join that recitation. I think we somewhat overextended the time a little bit, but um, maybe you get the idea of what the attention architecture is. There are few more slides and some stuff about like foundation models. Maybe we can cover that in the recitation. Okay.